My name is Charlotte Michaluk, and thank you all for this opportunity to share today. So, for the past few years, I have been studying different aspects of cargo ships, making them more economical, safe, and environmental. 90% of global trade is moved by cargo ships. If you look around and count 10 items, 9 of them may have been on a cargo ship at some point. We probably do not spend a lot of time thinking about cargo ships, but they are not subtle. This is the 200,000 deadweight ton Suezmax container ship. To give a sense of scale, if there is a person standing on the bow of the ship, we cannot see them. See the exhaust stack with the particulate matter coming out? I am working on an innovative way to reduce these emissions because they cause climate change and damage to human health. This research focused on developing a computational fluid dynamics model to optimize and solve an engineering problem, then building and testing a prototype. Each rectangular prism on this container ship is a TEU, or 20-foot equivalent unit. There are 20,124 of them. We often see them on the road as trucks. Cargo shipping remains out of sight on the 3/4 of the planet that is not land, unless things go sideways. You may have seen this ship, the Ever Given, in the news this week when grounded and lodged in the Suez Canal. This is quite the predicament. What's interesting here is that the size of the ship was a contributing factor in the ship grounding in high winds and also being difficult to refloat. It is a 1/4 mile long. Look at the excavator on the right. The reason why this ship was built so large was to take advantage of the physics to improve the cost and efficiency of transporting goods. At a design speed of 22.8 knots, it burns around 140,000 gallons of heavy fuel oil per day and 11 cycler, 80,000 horsepower, low-speed 2-stroke crosshead diesel engine. Just as this ship has reached the limits of the Suez Canal, cargo shipping with fossil fuel technology is also going sideways and reaching our planet's limits. Cargo shipping creates 4% of global climate change emissions and black carbon, and is linked with enough asthma cases to match 85% of the population size of New Jersey. These sustainability challenges make for an exciting time for cargo ship naval architecture. Our desire to use raw materials from around the globe or take advantage of relative efficiencies in production shows no signs of slowing. Therefore, our global cargo fleet will persist. Engineering solutions abound, however, many are costly, add complexity, and may even have unintended side effects such as reduced cargo capacity, increased maintenance, and water pollution. I researched Flettner rotors and scrubbers and developed a novel way to combine them. Flettner rotors harness wind power through the Magnus effect, while scrubbers recently became more popular when the IMO restricted the amount of sulfur exhaust emissions. However, an issue arises with the addition of these technologies. Since the primary purpose of cargo ships is to transport as much cargo as possible, any technology that occupies onboard space means we need more ships and more trips. This is inefficient and wasteful. My solution to this problem is the Flettner Vortex Scrubber. I had to design a special exhaust scrubber and use some principles of vortex separation in order to do that. The Flettner rotor harnesses wind power effectively as an auxiliary propulsion source. The vortex scrubber removes particulate matter without reducing cargo space or increasing maintenance costs associated with land-based scrubber designs. The exhaust scrubber is of low density compared to tanks or other shipboard mechanical systems, which makes it ideal to locate above the center of mass without significantly increasing the metacentric height and affecting the ship's stability or seakeeping. The Flettner Vortex Scrubber both harnesses wind power and cleans exhaust in a way that maximizes revenue, gathering cargo space, and minimizes operating costs, while mitigating climate change and respiratory illness. In the first phase, I used CAD and CFD to model my Flettner Vortex scrubber to maximize centrifugal force and minimize pressure drop. I gathered data and plotted a logarithmic chart looking at the range of exhaust velocities going from the engine to the scrubber. In phase 2, I constructed a Flettner rotor prototype. I measured the Kuta-Joukowski force generated by the Flettner rotor. In phase 3, I tested my prototype scrubber to measure its efficiency. I can offer a quick demonstration of the Flettner rotor functionality in my prototype. This is a 1:39 scale of a Panamax cargo ship with a Flettner rotor aspect ratio of 1:6. Flettner rotors generate 10 times more force than sails with the same area. And now I'm going to have it move back towards me. So this is definitely something that I look forward to exploring more. One of my next steps is to build a seaworthy scale prototype to test in protected waters like a harbor. Thank you for listening.